Hello everyone. Welcome to the instructions for the fifth lab. In this lab, we are going to work on the ways to implement the transformers or the circuits having the mutual inductances. So to solve this lab particularly, I have chosen this circuit from your homework. You have this in your homework 5. This was one of the problems where you have two inductors, primary coils having 1 Henry of inductance of 1 Henry, while towards the secondary we have the same 1 Henry, and the K1 is 0.64 while the K2 is 0.82. We are required to find the V1, V2 and the average power delivered to both of these V1 and V2. So that's the whole scenario. This is what we are going to find out in this lab. For this, I've already started. I mean, at least you will know how to implement the dot version. You will find out how to implement the mutual inductance defined by these K values, and you will be able to see how to compute the power in a little bit different way. One thing I'll show you how to implement the ground on one side of the primary only towards the secondary. You will see that how we will always be finding out the voltage across a component instead of putting a lot of grounds, because grounds, as I've been telling you guys, is kind of short-circuiting some of the nodes which are called as reference. You will also see that how inductors, when defined in the form of a mutual inductance or in a transformical situation, how do you define the series resistance with the coil to implement? Otherwise, you will see the errors in your Cadence simulation. So here's the open schematic. I'll quickly look into the, so we have 4 inductors. All right, so I'll instantiate inductors, the regular inductors that you've been using. In the inductors, we see the dot on the top for the first inductor, so I'll put the inductor as here. If you can see, if you can see that there's a dot here, dot on the top. All right. And then for the second inductor, the dot is towards the bottom. So I'll go rotate, use R to rotate, and then we will just put this inductor over here. And then if we look at the secondary coil, we'll see that the first Henry, the top coil has the same configuration for the dot, so I'll just put it over here, while the dot for the fourth one is again rotated, so I'll rotate using R, and I'm gonna put it over here. Now we have 2 resistors and a power supply. So for 2 resistors, I'll instantiate the resistor 1 over here and the resistor 2 over here. All right, I'll fit the schematic. So we have our 4 inductors and we have our 2 resistors. Now we'll define our voltage source. So I'll instantiate the V sign. Okay, and now we can quickly wire the circuit. So let me wire it. Okay, now towards this end I'll wire. Okay, All right, so I've wired the circuit. Let me fit the circuit. Okay, now if you see that the first inductor here, the primary coil is related with the secondary coil through this mutual mutual inductance coefficient K1. So we will be able to define within the analog library this mutual inductance coefficient, and we will relate these two coils together. Similarly, we are going to make a relation between these two coils. As you see, the K2 is 0.82. So to do that, I'm going to instantiate from the analog library something we call as mind. It's a mutual inductance. So mind 1 point over here between these two coils, and I'll just rotate it, and another mind over here. Okay, now if you see that the K0, the first K1 is 0.64, and it relates these two inductors. All right, 0.64. So our inductors representation over here is this one is L0 and this is L2. All right, L0 and L2. So I'll Q, hit the Q. The coupling coefficient is 0.64, while the first coupled inductor is L0 and the other one is L2. This one is L2. Okay, so this is 0.64 and we have related these two. The K1 is 0.82. Okay, so and the inductors are L1 and L3. So I'll start with the second one, which is L3, and then we have the L1, and this one here is 0.82. 0.82, right? So we have defined these coupling coefficients between these two inductors. This is very important. Please remember how to put the dots in here and how to relate these inductances. Now for this voltage sign, the solution, actually I have the instruction circuits was here. Okay, forgot to open this one. Here's the level 5 instruction circuit. So since we have again, as you know, in Cadence, I've been telling you that we work with the sinusoid waves. That's why we implement V sine. This is the cosine, V cosine. Since as I said that, I mean, all the phases are relative to the main power supply, so the same case is here. So I'll just use the cosine as the sine with the zero phase, so that'll work. Omega is 5 radians per second, so the frequency will be this, while the amplitude is 4. I'll go with the Q. Sorry, hit this one, hit the Q key for the properties. Where is the amplitude? Here, the amplitude is 4 and the frequency is 5 divided by 6.28. I took a precise number, 6.2832. 2832. All right, that's the frequency. And then let's go. Okay, I'll define the resistors first. So resistors are 1 and 2 ohms. All right, this is Q. This will be 1 ohm. This one is going to be 2 ohms. Okay, now let's define the coils. So all the inductors are 1 Henry. Okay, so that makes it easy. So I'll go here, I'll hit the Q key, and I'll select 1 Henry is a default unit. And then for the resistance, please define 1 micro as the resistor. Okay, so this resistance is important because to solve this equation analytically behind the scenes, the Cadence needs this. So I'll define this way. Similarly here, I'll go Q, it will be 1 micro, while this will be 1 Henry. Q, 1 Henry, and then 1 micro is the resistance, series resistance of this. Q 1 micro, while this one is 1 Henry. Alright, now all of our circuit is defined. Let's label, hit the L key to label the circuit. So I will be labeling the V supply, voltage supply, and then I'll label the VR, no, I'll not call it VR1, I'll call it VR0, and the bottom one as VR0, and then VR1, and then VR, okay, let's define this first. Actually, I have to define the ground too. So I'm going to define this one as V source. This one will be my VR0, and I want to define this one as VR1. All right, and then I'll define this one as VR2 and this one as VR3. Now this is important. Let me instantiate the ground first, and I'll tell you this technique to make sure you, every time you get the power right, just one ground towards the primary is more than enough for solving the circuit. Now in this circuit, make sure that instead of defining a ground, because these dot conventions, the dots are very important, you cannot enforce the ground, because if you force the ground anywhere, you are actually telling the system that this ground is connected physically with any ground that you define. So to avoid that, what we will do, we will always define the voltage drop across the component. So to define the voltage drop across the component, I'll need this node voltage and this node voltage. So I'll not be defining a ground towards the secondary. All right. Similarly, I'm going to define this one as VR2, which is the resistance here, VR2, and then VR3. Okay, so something like that. But this naming has to go in a specific fashion. So I'll call it VR2 and VR3. So this is my VR2 and VR3. So my voltage drop across this resistance will be VR2 minus VR3. Similarly, the voltage drop across this one will be VR0 minus VR1. This is very important. Once this is done, please hit the check and save. Any error? No error. I'll fit the... Alright, this is defined. Let's go launch ADXL. Create a new view. ADXL, sorry, what happened? ADXL, okay. Hit the test. Lab 5 instructions. Yes, that was the name of my file. You have to go and set up the environment as a 64-bit binary. Okay, you will define the AC simulation test, which is a transit simulation. Our frequency is nearly, what was the frequency? Like 800 millihertz, so which means like I can simulate this circuit for let's say because there will be transients in the beginning, so let me just simulate it for 60 seconds or for one complete minute. I'll hit the conservative. Okay, all right. Once this is done, I'll set up the outputs. In the outputs from design, I want this VS, I want to see VR0, VR1, so that I can define their subtraction later on, VR2, VR3. I want to see all these plots. And then I want to see the, do we have in the lab 5 instructions? Okay, the voltages V0 will be defined here. V1, V2 we can find out. So we'll look at the current going through the inductor. We will also look at the current because we have to find the power. So I'll be defining the power going from top to the bottom, So I've defined the current going into the resistor, and I'm just not sure. I'm just choosing this one of the current value, right? For the power supply, hit the escape key, go back to your setting outputs. All right, okay. We'll go to ADXL and we'll now run the simulation from here. All right, run the simulation. Let's see. Okay, we have the plots. Let's look at, I'll take the new window. Let's quickly plot all of them. Okay. Beautiful plots. Okay, I'll turn off everything and I'll start verifying the peak values from our instruction circuit. From the instruction, we have the primary current. Okay, it was good that I found I chose that one. So the primary current is 0.74 amp, which will be V0 plus here. This one is this the one? Okay. Let's see. That's not the primary current is through the inductor 1 and L0, which we did not choose, I think. Okay, let's find the other current. I mean, the current, finding the current is not part of the problem, but I just wrote it as a confirmation because while you were solving this in homework, anyways, you wanted to find that. So I1 was defined here, so that I1 is the one which goes through the 1 ohm resistor. So let's go to 1 ohm resistor as R0 is the 1 ohm resistor, right? That is the current again. So that's 466 milliamps of the current, which is here 466 milliamps of the current. And then the second current, here 460, and then the I2 is like 566 milliamps here. Yes, this is 565 milliamps. And now if you see very closely, you will see that they are off by a few degrees. All right, the phase shift between these two are very teeny tiny, and if you can see actually the phase shift here is 118 and minus 51, the phase difference between these two currents. This can be observed in our, this teeny tiny phase can be observed here. You will be able to see that. I'm just this is not part of the problem. I'm just showing you that how our simulation follows the analytical instructions or the analytical solutions, or vice versa. So when you see there's a phase difference, and so that is actually shown here. Okay, these two things are gone. Now look at the things we want to find. We want to find the V1 and V2. These are the two things required. All right, so V1 is okay, let me turn off this here. So my V1 is the, as I said, that it is the difference between these two VR0 and VR1. All right, that's the transient difference between these two signals. So we can actually go and find out. We can say that plot new window, yes, direct plot transient difference between VR0 and VR1. Just plot this. All right, let's see. The system has plotted this. Yes. And if you see the peak of this one is 466 millivolt. All right, 466 millivolt. And in instructions we can see that this is 406 0.4681 millivolts. Similarly for the other one. So please make sure when you're measuring the voltage across the component, especially when you're dealing with the mutually the circuits involving the mutual inductance, always go for the voltage drop or the transient difference like we did here. So I'll again go to the direct plot, and then I'll go transient difference between VR2 and VR3. Oh, it's going to replace our old plot because it was a new window. All right, it's a new window. Okay, so that's our new window, and as we see, the voltage here is 1.13 volts, which is again confirmed 1.13 volts. So actually, instead of new window, let me go here. Instead of new window, let me append the previous plot, because I want to again look at this difference of 10 degrees, if it is visible, the phase shift between these two. So append, and again directly plot, go to the transient difference, and I will plot it again, VR0 minus VR1. So it is going to append on our this plot, and we'll be able to see, yes, here. Yes, it's visible. We can see that. Let me change its color. Thick. All right. Okay. Yep. You can see that actually there's a very small difference, not very much visible, which is actually, I mean, justified for this signal. It's not visible again here. Here you might be able to see that the moment this wave is at 0, this wave still needs some time to come to 0. So that's again, there's a very small shift, and which is observable, and we know that this is 466 millivolts and this is 1.13. So this it is fixed. We can see that this is what we require, and now we're looking at the power dissipated at these two resistors. And for that, we'll use a calculator. So we'll go to the ADXL, sorry, and then go to the tools and go to the calculator. In the calculator, I'll look into the current. Here's the plot. Okay, for the calculator, let me do this. Let me first of all, this is something new for you guys. I haven't taught you this before. I can go to the calculator here, and then I can say that give me the transient difference, which is this one. Okay, give me this transient difference. Just type in the command from here. So VT is colon and then slash VR2, sorry, slash VR2 minus VR3. All right, I'll send it to the buffer. Okay, now the next one is VR0 and VR1, and now send it to the buffer. So I've sent two expressions to the buffer. Let's go to the buffer. Here, output setup. Okay, the first one, let me name it as, now please, this is important. Everybody who is listening to the lecture, everybody is listening to the lecture, this is important. When you will be evaluating these expressions, this window will be the part of your lab report submission. Please note that this is going to be the part of your lab report submission once the evaluation has been done. So I'm going to call this VR2 minus VR3. What was VR2 minus VR3? So VR0, this one will be called as V1, and we are going to call this one as V2. All right, as per the section, this was V1 and V2. So VR0 minus VR1. VR0 minus VR1, that is our V1, while this one is V2. All right, we are going to call them this. So go to the results, go to reevaluate, and you have found again the differences of these two plots in here now. Okay, now these are the two expressions they have calculated. Now we have not done that last time. I'll show you here. Now you can actually use this V1 and V2 naming from here as your direct expression. So what I mean by that, we are looking at the current, the power of the R1. So that is my power. I'll look at the current going through R0, and then R0 will be then multiplied by the what was the name? Sorry, what was the name here? VR0, VR1 is V1. All right, so that V1 value is already is taken from this expression. All right, internally the system is going to embed that. That will be the V1, and I'll send this to the buffer, and then I'm going to send the next current again from here. This current multiplied by V2, and send it to the buffer. I'm going to call this as a what is it? This is not a power, so I still need to average out this. So instead of sending them to buffer, I'm going to first of all clip this. Where is clip? Here. Let's clip it for from 20 to 55 seconds. Okay, that's okay. We have simulated for 60 seconds, so I'm taking 20-25, and I'll average it out to calculate the average power. So here's the average for the same seconds. Yes, okay. I'll send it to the buffer, and then for this expression, I'll go to the calculator again, and I'm going to clip, okay, and then average it. Sorry. And I'll send it to the buffer. So these are the two expressions. So I'm going to call them as power of R1, average power, and this will be power underscore R2. All right, we can go to the results, and before that, let's just delete these two. I want to delete this output, and I want to delete this output. Go to the results, just hit the new window and evaluate, re-evaluate, sorry. And re-evaluation gives us our resistor R1 as 319 milliwatt. Okay, we have 322 milliwatt, while the P1 is 109 milliwatt. We have 108.6 milliwatt. Okay, there it's just the matter of choosing the V1 and V2 wrong. So I've chosen this one as power R1, while this is power of 2 ohms. So because this R1 does not represent the 1 ohm or the 2 ohms, it is representing the resistor 1 and resistor 2. All right, my resistor 1 here is this one, which is 1 ohm. So what I'm saying, that it's not switch, it's just a naming convention. Okay, the naming is different here. So we have seen that we have find out the power as per the problem solution that you have observed. Again, please make sure that this, after the evaluation, this window is part of your submission. This is very important. Do not forget, this is going to be the part of your submission. Let's quickly look at the, so we've looked at everything, and everything is in order for this circuit. We have seen the voltages, peaks and currents and everything, and you have seen how to make the voltage here, and then you can use it further for the expression even within the calculator. Okay, once this is done, I'll quickly go to the problem. So these are the two problems. So we have one with the K value, and I want you to find out the average power absorbed by each resistor. There are two resistors. Similarly, the voltage drops, okay, across both the resistors, V2 ohm and V0 ohm. Again, voltage drop across is a peak voltage. That's what I'm talking about here. Okay, you have 1000 as an omega value, so you can find out the frequency for this circuit. For this circuit, and Vs is 8 cos of 1000 t. It's mentioned here. Again, the problem is from your book. Now go to the second question. This is again your homework problem. It's from your homework 5 here, but in the homework 5 they just want you to calculate write the expressions here, okay? But I've asked you guys to actually do the analysis. I want you to find out the power of each resistor and what is the peak current through 6 Henry inductor. This is an important question, all right? And then the omega for this question is 2 radians per second. Please note that the mutual inductance between these two is 0 Henry. You will have to plot the voltage drops across all resistors like we've done now, and you will just look at the current through the 6 Henry resistor. For the other currents, for the power evaluation, of course, as I've told you guys, please make sure that you are showing this evaluation window with the results evaluated, all right? And of course, definitely with the plots. For this, please note that this 100 is a peak value, all right? This is not an RMS value. This is going to be the peak value, which you set as an amplitude, which was given as 4 in our this problem that we solved, 4, okay? Just treat it as an amplitude. Anything else? These are just two circuits. I did not ask you to put a lot of plots, just few plots from here, a few plots from here, and the power dissipated to the resistors, and that'll be all. Please make sure when you're putting the inductors, always add in the resistor, the series resistance. Choose it as 1 micro ohm, and make sure that the dot convention is fulfilled. You should take respect how the dots are there to get the right answers for your questions. Okay, thank you very much, everyone.